Theory and Fundamentals on Enzymes, Substrate and Reaction. All complex biochemical reactions such as the transfer, synthesis or breakdown of molecules that occur in animals, plants and microorganisms are regulated by enzymes. Enzymes are usually described as biological molecules, which are proteins and some RNA molecules that increase the rate of various reactions that occur in the biological system without being used up. Indeed, enzymes do not participate in the actual reaction. They possess an active site in which the substrate will bind and form enzyme-substrate complex. Notice that the binding of the enzymes and substrate is very specific and depend on the structure and conformation complementary between the enzymes and the substrates. Enzymes catalyze reactions by lowering the activation energy of the reaction. In other words, it will reduce the required amount of energy needed for the reaction to occur, thus fasten up the reaction. The rate of reaction can be affected by the changes in substrate concentration, temperature, pH, and presence of a competitive inhibitor. The study of these factors affecting the activities of the enzyme is known as enzyme kinetics. Our experiment focuses on the enzyme kinetics, which are the effect of temperature and pH of rennin using milk as substrate. Rennin, also known as chymosin, is a proteinase that accelerates the coagulation of milk protein in the stomach of some animals. As a proteinase, the primary role of the enzyme is to hydrolyze peptide bond of amino acid in casein of the milk. Noted that there are 4 types of casein molecule: alpha S1, alpha S2, beta, and kappa. Rennin broke down K-casein to para-K-casein and small molecules called glycomacropeptide (GMP), as shown in this equation. This process is heat sensitive. At low temperature, the rate of the reaction decreases, while at high temperature or room temperature, the reaction will speed up since there is more collision of molecules which might lead to collision of the enzyme with the substrate. However, at very high temperature, the enzymes are denatured and reshaped. The substrate will no longer fit the enzymes. It is also affected by the optimum pH values of rennet, which is 6, coincide with the conversion of K-casein to para-casein. The materials and equipments used in this experiment are chopstick, rennet powder, measuring cups, milk, thermometer, hot water, ice cubes, big bowl, small metal cup. Methodology. First, we have to make the enzyme solution. For that, we mix rennet powder to 100 ml of water and let it aside. Then we put 30 ml of room temperature milk into the small metal cup. We choose metal because of its great thermal conductivity. Temperature at 33 degrees Celsius. To bring the solution at a temperature of 33 degrees Celsius, we pour hot and room temperature water into a big bowl and we put the metal cup into it. We shake the metal cup to fasten the heat transfer. Then we check the temperature of the water bath as well as the milk. When the milk reaches the required temperature, we add 5 ml of enzyme solution to the milk and mix thoroughly with chopstick. Right after that, we have to immediately start the stopwatch. Then we occasionally check the temperature of the solution and the one of water bath. And then, stir the milk to check whether there was formation of curd. We shake the cup from time to time. After curdling, we stop the stopwatch and record the duration. We will use the same process for a water bath of 44 degrees Celsius and 60 degrees Celsius. Temperature at 44 degrees Celsius. To increase the temperature of water, the amount of water at room temperature added was less compared to the first one. The water bath used was initially at 53.5 degrees Celsius and the milk at 42 degrees Celsius. We shake the solution until it reaches 45.9 degrees Celsius, then we add enzyme solution and mix it properly. We start the stopwatch and occasionally shake the solution and check its temperature. The curdling started at 44 degrees Celsius and the time taken was recorded. Temperature at 60 degrees Celsius. The water bath is made with only hot water. We put the enzyme solution at 63.5 degrees Celsius and then we stir occasionally. The solution did not curdle. Temperature at 22 degrees Celsius. In here, we are not going to use water bath. The milk will just be left at room temperature. When the temperature reaches 22.4 degrees Celsius, we will just add the enzyme solution, then we mix it properly with the milk. Start the stopwatch. Temperature is checked regularly and to check that there is curdling, we shake the solution. Curdling occurred, then we stop the stopwatch and record the duration. Temperature at 16 degrees Celsius. In here, we want to reduce the temperature of the milk, so instead of hot water, we will add ice cube to the warm water. We will add the enzymes solution when the temperature reduces till 15.9 degrees Celsius and then we stir gently. Start the stopwatch once again. Then we wait until it curdles and then we record the duration. Discussion. So as we said before, Renin broke down K-casein to para-K-casein and small molecules glycomacropeptide (GMP). This happens because the hydrophobic casein micelles, which the K-casein, have the tendency to aggregate, but they do not, due to the presence of glycomacropeptide and negative charge on the micelles. The active site of the enzymes contains two highly conserved aspartate residues. Initially, one aspartate residue carbonyl is deprotonated and the other is protonated. The deprotonated aspartate activates the water by abstracting a proton. allowing the water to perform a nucleophilic attack on the carbonyl carbon of the peptide bond in the substrate, forming a tetrahedral oxyanion intermediate on the substrate that is stabilized by hydrogen bonding with the second aspartic acid. Rearrangement of the intermediate causes the protonation of the amide on the substrate, completing the cleavage reaction of the substrate peptide into two product peptides. There is also a water molecule associated with the peptide bond that is cleaved. So, during the hydrolysis of K-casein, the K protein lose their glycomacropeptide water-soluble tail and become para-K-casein. The para-K-casein is not strong enough to maintain stability of the micelles. Therefore, when the other casein molecules coagulate in the presence of calcium phosphate and become bigger enough to make a continuous three-dimensional network, the K-casein can no longer keep the other casein separated to prevent aggregation. From the recorded data, we can plot a graph showing the effect of temperature on the process. We can see that at temperature 16 degrees Celsius and 22.7 degrees Celsius, the temperature is considered low for this enzyme. So it took 1500 seconds and 600 seconds respectively, indicating the decrease in the rate of enzyme reaction. Increasing the temperature to 33 degrees Celsius, which is relatively high, results in increment of heat, which, as we know, increase in molecular motion since the reactant molecules begin to move faster and become more likely to collide into each other, causing a reaction between the enzyme with the substrate. This speeds up the effect of enzyme activity, reducing the time taken for coagulation to 60 seconds. However, when we increase the temperature to 44 degrees Celsius, the enzymes start to denature, which causes the shape of enzyme and its active site to change, making the substrate unable to bind with it. This slows down the rate into 150 seconds. After denaturation completes, as in 60 degrees Celsius, the enzymatic activity of renin has ceased altogether, and no coagulation is formed. We can conclude from this observation that this process is very heat sensitive and the optimal temperature with the highest rate is at 33 degrees Celsius. pH also affects the stability of the enzyme and consequently its activity. In unfavorable pH, the excessive hydrogen or hydroxide ions may break the ionic bonds that form the protein or interfere with the reaction at the active site. Reshaping of the enzyme and its active site lowers the catalytic activity. In favorable and optimal pH, the protein is stable and has the highest enzymatic activity. Rennet activity is stable and able to coagulate milk at the normal pH of milk, which is high pH, and its activity increases with decreasing pH. Effect of pH on the coagulation of milk using rennet enzyme. Materials and equipment. 1. Big container. 2. Hot water. 3. IR thermometer. 4. Litmus paper. 5. Lemon squeezer. 6. Sodium bicarbonate powder. 7. Chopstick. 8. Lemon. 9. Metal muffin tray. 10. Full cream milk. 11. Measuring cup. And 12. Coagulation powder. The muffin tray will serve as container for the milk. Pour 20 ml of milk in 3 muffin cups tray and check the temperature of the milk. Using a litmus paper, check the pH of the milk. pH exit. Then, in the first cup, add the slightly diluted lemon juice and 5 ml of enzyme solution and mix properly using the chopstick. Use a litmus paper to check the pH of the mixture. Record the duration of the clotting. pH basic and pH neutral. In the second cup, add the bicarbonate of soda solution. Check the pH of the solution. Add 5 ml of enzyme solution in the third and second cup and mix properly. Check the pH of the third solution and gently stir the solutions. Do not forget to clean the chopstick before using to avoid contamination. And record the time needed for clotting. This is the result of the experiment. pH and the coagulation time in minutes. Thymosin is more stable at pH values between 5.3 and 6.3. Coagulation at pH 7, which is near the optimum range, will result in a fast activity, which is only 2 minutes. Reactions with pH condition outside this range will decrease the enzymatic activity. At alkaline pH values at pH 9, the duration increases by 4 minutes. This loss is due to an irreversible conformational change. Under acidic conditions, such as at pH 2, the enzyme loses its activity rapidly, probably caused by auto-degradation. However, results show that coagulation at pH 2 is even faster than pH 7. This is because of the exposure to acidic elements like vinegar, lactic acid, and in this case lime juice, is affected by the lactic acid which coagulates the milk. That is to say, the coagulation was done by the acidic element, not by rennet. Another probability is that the coagulation is caused by pepsin, which is more suitable in low pH since most rennet preparations contain small amounts of pepsin. There was decreasing rennet activity and increasing activity of this pepsin as the pH was decreased.